previously I was looking at a flat surface, for instance, that lied in the XY plane. That was what I was using to make some arguments about simplification and give you some examples. There's no reason that our surface needs to be flat, and eventually we're going to get back to closed surfaces. Right now we're just trying to talk about flux in general. Later we're going to tie it back to our closed Gaussian surfaces. So most of the time our surfaces that we're interested in are going to have one or more curved pieces. So we have to think about what that means. Now this is a case where I'm not going to do out any really complicated mathematical examples. If you've had multivariable calculus, you might be able to think of some situations where you've done some of this math. This is a case where we have two simplifying situations, and I'm 99% of the time you're going to be able to use one or the other. So we still have the same equation. Again, this is really general. Now our surface doesn't lie in the XY plane, it's all curvy. But our little differential areas are still little tiny squares that we would assume our electric field is constant over, and we would assume our square is so tiny we can consider it a little tiny flat square. So again, that's the magic of calculus here, but if our electric field is varying with our surface, this then is a little more complicated. But let's think about the situations where this is going to be simple, because again, I can give you infinite scenarios where this is impossible to do by hand, and only a few situations where it's really challenging to do by hand. So let's look at the two situations where it's easy. And these are our two primary simplifying cases. And we'll talk about each of them individually, but first we have an electric field that is tangent to the surface everywhere. It's a little hard to see that here with this 3D view, but imagine that we have a side view of our surface. At a given point, your electric field is there. At a different point, your electric field is there. You know how tangent works. It's just a little hard to see here. On the other hand, we could have the electric field being perpendicular to the surface. And in this case, we want it to have the same magnitude at each point. Now, cleverly, in A, we could have same magnitude, like maybe E is constant or not. Here's what's great. In A, the flux is 0, regardless of whether E is constant or not. In B, we definitely want E to be constant, or else it's going to be a little harder to do. So again, what we're talking about here is it being perpendicular to the surface everywhere on the surface. So let's look at how this simplifies, and again, what this might look like in these two simplifying cases. So for the case of it being tangent to the surface, this is when we're going to have a circular field. Now you might say, hey, wait, when on earth are we going to have a circular field? I don't think we've drawn any circular field lines yet. And you're right. Notice we have not actually seen a case yet in electrostatics where we have a circular electric field. We are going to meet circular electric fields later when we talk about certain situations in electromagnetism. And again, what we're talking about right now with flux and these surface integrals, this is also going to apply to magnetic fields, and you get circular magnetic fields very often. So it might seem like this is a case that we're not necessarily going to have. The other thing, though, is you could imagine a circular field maybe in only a place. And so here it's curving in some way, but maybe it's not going to be perfectly circular, or maybe this is only one portion. So again, circular field overall is kind of a big simplification, but there will be cases that we use this. Since the field is always tangent to the surface, this dot product is 0. Once you have this equaling 0, the whole thing equals 0. We can integrate 0 over whatever surface we want, and if it's 0 everywhere, well, your flux is 0. So this is the nice thing. What you're looking for is if your field is tangent to the surface everywhere, then your flux is 0. Nice and simple. You don't even have to worry about your magnitude being constant or not. So now, another situation that we're actually going to use right away, and that's a little more complicated to think through, is that our electric field is perpendicular to the surface. Now, for this simplification to work, we need it to have the same magnitude at each point. In that case, when we go to do the dot product, theta is equal to 0, so cosine of theta is equal to 1. So we just get to multiply. And once we multiply, if we then say that E is constant, we get to pull it out. So E comes out in front, we're integrating over our surface, dA, and we've dropped the vector symbols because we've taken the dot product, but that just gave us cosine of theta equals 1. And we said that integrating dA over the surface is equal to A. So that's why we say that the flux in this case is equal to EA. So as long as you have an electric field that's perpendicular to the surface and has the same magnitude, you're allowed to just multiply them. But now recognize that we're going to construct some more complicated situations, so you would only want to multiply them when these conditions are true. So you might have a very complicated surface where you need to break it into different simplifications, different categories. So here we reach a really important tactic, and this is going to be for evaluating surface integrals. We're going to see them a few different times in this class, and again, I recognize that you've maybe not done surface integrals in a math class before. That's okay. You're going to see some new notation, but you can handle this. And the reason you can handle this is we're really going to be limiting it 99% of the time to 2 simplifications. The first is that the electric field everywhere is tangent to the surface, so you get to flux equals 0. Second is everywhere it's perpendicular and has the same magnitude, then we're multiplying. And again, you might have a complicated surface that you break into points and break into pieces, and so maybe for some of the pieces number 1 is true, and for some of the pieces number 2 is true. But recognize that these simplifications will get you pretty far, but this is part of why we need to think about choosing our surface correctly and thinking about the symmetry of our field.